Okay, let's look at some examples from section 3.1. The first one we're going to look at is number 2 from your homework. It's just a nice, simple differentiation problem. So all we're looking for is what f prime of x is, what the derivative of this function is. And I picked this one specifically because this highlights the difference between a power function and an exponential function. We see those two different types in this one equation, and we're going to see how the derivative rules are different. So if we look at that first piece, remember, because of my sum and difference rule, I can just focus on each piece individually. So my derivative of x to the fifth, I'm going to use my power rule to find that derivative, because x to the fifth is a power function. It's a variable raised to a constant power. But my other term is an exponential function, and you'll notice it does have a coefficient in front. And we know based off the constant multiple rule of derivatives that I can just keep that coefficient there and just focus on my function e to the 4x. So this is an exponential function because your base is constant, e is constant, and the variable is in the exponent. So I'm going to use my exponential rule. Well, you'll notice here I have e to not just x is being multiplied by a constant, in this case 4. So I'm going to use that derivative rule that we learned in our concepts video, where if I have the derivative of e times a constant times x, you get the same exact thing multiplied by whatever that constant was. So my derivative of this piece, I get 4 times e to the 4x. And now I can simplify if I want to by just multiplying the 8 times the 4, and there's my derivative. Okay, let's move on to a more involved problem. This is number 8 from your homework, which is the last one. And this is just a good applied problem where the function that we're working with represents a demand function for a certain music player. So the product is a music player. And if you look at this function, hopefully you can see why it qualifies as an exponential function. We have a base that's constant. E is a constant value, and the variable is located in the exponent, making this an exponential function. And so this problem asks a bunch of different questions related to this scenario. And the first question is just, how many music players will be bought at a price of $230? Do I need the derivative for this question? No, because remember, the derivative is all about rates. And this is just asking me how many music players for $230. That's exactly what this equation tells us. It tells me the demand for a specific price, which means to answer this, all I have to do is plug 230 into my equation. And then using my calculator, I can find the value of, in my case, 63.673. So that's what I get when I actually plug it into my calculator. Remember, with exponents, a common mistake here is don't multiply those two numbers first. Don't do 160 times e and then raise it to the exponent, because then you're breaking the order of operations. With order of operations, we always do my exponents first before doing multiplication. Well, regardless, so that's my value, but just be careful when you're putting your answer in, because first off, the demand is in thousands of units. So it's not that the demand will be about 63 music players or rounded up to 64 music players. This is in thousands of units, which means this is 63,763 music players. But Pearson does ask you to round to the nearest thousand. So if I move my decimal place for it to be in terms of thousands of music players, I then need to round to the thousands value, which is this one. And so my next number is a 7, which means I need to round it up, and that gives me approximately 64,000 music players. Right? That's recognizing that this number is in terms of thousands, and then you're rounding to the nearest thousand. Okay, so that's part B, or sorry, that's part A. Part B just wants me to graph this function. It does specify a specific domain, so when I graph this, I'm going to start at 0, so I'm just going to graph this first quadrant. Well, if we go back to my equation, you'll notice that my equation has a coefficient of 160. And if we remember from the concepts video, that coefficient actually represents my starting value, or my y-intercept. So I know where this graph starts. This graph starts at 160, or 160,000. But now I need to figure out, is this a decay function or is this a growth function? Well, if I look at it, I might think, oh, hey, since e is greater than 1, that makes it a growth function. And that would be an easy mistake to make, but that would be ignoring the fact that there's a negative in my exponent. And remember, if your base is greater than 1, but you have a negative in your exponent, this ends up actually becoming a decay function. So, since it's a decay function, I shouldn't be growing, I should be decaying. And you'll notice as I draw this line, am I having it hit the x-axis? Am I having it reach 0? No, because exponential functions, as long as they haven't been shifted up or down, exponential functions will never actually reach 0. Okay, moving on. Next, it wants me to find the derivative, q prime. Well, let me rewrite the derivative down, or the original function down here so that we can look at it easier. There's my function. This function has a coefficient, has a constant multiple. And so according to my derivative rules, I can just keep that 160 there and just focus on this piece. Well, this piece falls under this category of e to a constant times x. Notice that's 2 questions from your homework, and both of them have this e to the kx form. What's my derivative of this? I get k e to the kx. So my derivative for this specific one is going to be negative 0.004 times e to the negative 0.004x. And now I can multiply those two together, and I get negative 0.64 e to the negative 0.004x. And I want to point out something. This derivative is negative. Remember, the exponential piece, this piece will always be positive, and so having a negative coefficient means the derivative will always be negative. Does that make sense? Remember, the function is a decreasing function, meaning that the slope will always be negative, and therefore the derivative should always be negative. So I just wanted to point that out real quick. Well, the last part is interpreting this derivative. What does this derivative actually tell me? Well, first off, we have to remember that what is a derivative? It's a rate of change. The rate of change of what? Remember, a derivative tells you how the output changes as the input changes. So the rate of change of, or in, q of x, because q of x represents the output. The dependent variable, or the function value, represents that output. So it's the rate of change of q of x is how much? Well, that's what the actual value of the derivative represents. The derivative is that rate of change. Since the output is 1,000 music players, that's what the derivative is telling us, per change in x. And in our case, what is x? X is price. So how do I change the price? I change the dollar amount. So in review, what does the derivative tell me? It tells me how that demand changes, how many less products will I be able to sell if I increase the price by 1. And that takes care of number 8. So good luck with the rest of the homework, and remember, if you have any questions, please reach out. But have a great day, guys.